All right, so today we are going to be uncovering the structure of an unknown using MS, IR, carbon-13 NMR, and proton NMR. So starting out with MS, we see a diagram in a chart um, that we need to go ahead and fill in. This first peak right here helps determine, which is the 166, the molar mass of the structure. And we also need to indicate what is the big peak. Whenever looking at MS, using this helps us identify what elements are in the structure and really just lays down the groundwork for us. And using the different peaks shows us which elements are where, and there are certain numbers that indicate certain elements or groups. For instance, we have a difference of 17 between the peak here, 28, 14, and 13, which helps us narrow down the elements, and with 166 being like the molar mass. So we're going to use the DOU formula because it does not look like we have any triple splitting or any patterns that would indicate a bromine, chlorine, or nitrogen. So we're just going to go ahead and say no bromine, chlorine, or nitrogen, and we're going to do the DOU formula, which is indicated by 2 times carbons, and we found the carbons using the diagram, and with 166 and a difference of 94, and using the independent peaks, kind of subtracting them out and coming up with the best formula, we are going to do 2 times carbons, which is estimated about 9, because we, after configuring this, indicated there should be about 9 carbons, and of course carbon is 12.011 for the mass, about 10 hydrogens, and since there were no chlorines, bromines, or nitrogens, we're going to say there are some oxygens, which is about 15.999, and there's about 3 of them, which all of this adds up to the 166. And we are also, oh, you can't see what I'm doing. We're also going to, with the DOU formula, it's 2 times carbon plus 2 plus nitrogens, which there are none, plus halogens, which there are also none, minus hydrogens. So that gives us 2 times 9 plus 2 minus 10. Oh, and this is all over 2. And then over 2 equals 5 DOU, which really comes in handy later on down the road. I misspoke earlier, and it's actually minus halogens and hydrogens, which there were no halogens to begin with, so it did not affect our DOU calculation of saturation, which is still 5. I'm going to move on to IR, and whenever it comes to IR, since we already know the elements that are in the structure, it kind of helps us break it down to identify the different function groups. With IR, there are 6 zones, with the last zone technically not being a zone. It's more of the fingerprint region, so we're going to focus on 5 zones of IR. The first zone is this area about here, and with this big dip, we know that really things out here are a carboxylic acid. With the second zone, there's another dip or peak, and we see this about here. And we know that usually around this region there are C to H bonds, and with the other peak being in zone 3, we see this right here. And this is from a carbonyl group, which could be anything from ketones to aldehydes. And we notice some peakage over here, and this is usually indicated by a C double bond O. And this business out here in this area, we refer as the fingerprint region because we don't really pay this any mind. So when it comes to IR, there are really only 5 different zones. And this helps us put together what we could consider and construct a structure for our known elements, which again is the C9H10O3. Now we're moving on to hydrogen NMR, proton NMR. And since we know that the structure could potentially have carboxylic acids, CH bonds, carbonyl groups, C double bond O, and we also know it's C9H10O3, we're able to construct a structure which would make sense of the different splitting from the proton NMR. So we're going to come up with a structure, and looking back at the mass spec diagram and looking here, we know that sometimes with the carbonyl groups or the aromatic areas in the IR, that we can kind of put together starting off with a benzene ring, which would eliminate quite a few of the carbons that we know are present. And we know that there are oxygens, there's at least 3. So we are going to go ahead and draw on an oxygen. So we're going to draw on an ester, because this, the structure, there are many ways to do the structure, but it needs to make sense with the splitting pattern. And we're going to connect it to the carboxylic acid that was present, with this being 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons, and then we have the hydrogens, of course, on here. We have the 10 hydrogens, and then we do have the 3 oxygens. So looking up here, we have the splitting, which this is indicated by 2 hydrogens. This also has 2 hydrogens because there are 2, even though they're really hard to differentiate, they're hard to see, but we do have 2 hydrogens, and it's also labeled on here as well. And with this, we have 5 hydrogens, which we can automatically assume that the 5 hydrogens, with the peaks being so clustered together, that it is referring to the benzene ring. So we're going to do a little bit of this, and bring this on up here, because there are the 5 hydrogens. And with this, we don't necessarily see the splitting since it's only protons. On the carboxylic acid, we are going to assume that the 2 splitting, since there are 2, and it goes off of the N+1 rule, and looking at the adjacent carbon, that we have this over here referring to one of the peaks, and also the carbon over here referring to the other one as well. You always want to look off of the adjacent carbon with the N+1 rule. So looking off the adjacent carbon, you count up the hydrogens, or the protons, I should say, and then add 1 and then stick it on there, and that's how we find the splitting. And of course, this again is the structure that we came up with that justifies the splitting and the proton NMR. Now we are moving on to carbon NMR, which we need to draw the structure, and again, to make sense of it, because unlike proton NMR, carbon NMR does not split. So we see some peaks up here, And going from left to right, we're going to label it in a descending order, starting with this one right here. And this being the furthest down field is going to be the most, it is going to be the most delocalized. So we're going to label this with 6 or 7, 6, 5, 4, 3, and we're not going to pay this one any attention. And we're going to do 2 and 1. Oh, I again misspoke. The peak down, furthest downfield this way is going to be the most de-shielded, not delocalized, de-shielded. And with the DOU, and also looking at the structure and identifying where the protons are, there are special environments. So looking at this, we're going to label, and I'm actually going to use a different pen for this color. We're going to label this area as a special environment. Since there are carbons on the benzene ring, and since this is an oxygen here and oxygen there, this oxygen, carbon, right there, is going to be the most de-shielded. It's surrounded by both the acid with the oxygen here and the double bond to the oxygen there. This is going to be the most de-shielded, so this is going to be the 7th peak over here. And going off of another one that would typically be probably the closest to an oxygen would be this one over here. And we're going to label this as 6. Again, corresponds to the 6th peak. And we're going to label, kind of fill in the rest, going in order of like descending. Since these are closer together, we're going to assume that these are around the benzene ring. So we're going to label this as 3, 4, 5. With 3 being the least de-shielded of the 3, so it's going to be a little bit further right downfield. And that leaves us with these 2 over here, with number 1 being the least de-shielded and number 2 being the second least de-shielded. So de-shielding works for carbon-13 NMR, whereas proton NMR uses the splitting method. So that is how we identify the structure and justify the structure that we identified. All right, thanks.